So now we have negative flux. We have a maximum, but it's negative. That's sort of interesting, right? So I can change this flux, and that's, by the way, what makes current flow, is changing the flux. I can change the flux by simply rotating this, can't I? Yeah? Yeah? In fact, if I sat here right now, this is positive flux, zero flux, negative flux, zero flux. It would oscillate back and forth, wouldn't it? Yes? In fact, that is why one of the reasons why we have alternating current flowing, because when we generate current, we do it almost always by rotating a loop of wire or magnets relative to each other, right? Okay? So this is it. This is the secret. Okay? This is Bonneville. That whole thing, when you go to Bonneville, they hold this whole thing about falling water and the energy of falling water. It's not that at all. Okay? There are people that sit there with these loops of wire, right? And they're just sitting there spinning them. That's what they do, 60 times a second, around and around and around, right? Okay? Yeah? They sit there and spin those loops. Okay? The other thing that they can do, by the way, is just like take the loop in and out of the magnetic field, right? Okay? But so stay in school, kids. Okay? Stay in school, because
Can you spin it 60 times a second?
well, I'm not, no, I'm not that good. I'm not saying I'm, better at this, Yeah, I went to school and I'm not, because I couldn't do this. I couldn't get that job, So there we have it, right? Okay, so this is a weird thing, right? Is that the area is that weird vector, okay? Area is represented by a vector like that, okay? Okay, now, how can we change the flux? Because changing the flux is what causes an EMF or a voltage to be imposed, right? Well, one way to do it is that we can change, obviously we can just change the magnetic field, right? The magnetic field could get stronger or weaker, okay? And in this case, I'm going to represent the magnetic field as the light from that projector, okay? Here's my loop, yes, okay? There's my loop, and if I just simply make the magnetic field change, if I make it brighter or darker, and indeed I believe I can make it darker, okay? Brighter, darker, brighter, right? Okay, if I did that, if I turned the magnetic field on and off or made it dimmer, I don't quite have the way to do that, right? Okay, then this thing we'd induce a current in this thing. Changing it either way would change it, right? I can also change the area of this thing, right? I can literally change the area, not rotate it, not change the brightness of the light or the intensity of the magnetic field, right? And so I could like make it bigger. There, it's a little bit bigger now, yeah, see that? Okay, or I can make it smaller. A little bit smaller now. See that? Amazing, right? Okay. Bigger, smaller, right? Okay. I can also change the angle, right? I can rotate it. Now remember, angle is a weird thing, right? It's the angle between the area vector. This is the area vector, right? Okay. Right now the angle is what? It's 0. I believe it's 0. We're getting all the possibilities. 0, 90, 270. It's 360. It's, I was adopted. Okay. No, that's not the answer. Okay. So anyway, there it is, right? The angle right now, the light is heading toward the screen. Isn't the arrow heading toward the screen? So the angle is 0, right? Now watch. The angle is now 90 degrees. Now the angle is 180 degrees. Now the angle is 270, etc. On and on. Here we go, right? Okay. So I can rotate this thing, and that will also induce flux. Yes. Okay, and then we can also do any combination of it, right? So in general, the change in flux is just your final flux minus your initial. It's always final minus initial, right? The amount you've grown this year is your final height at the end of the year minus your initial height. Yeah. A theoretical concept that lets us calculate EMF. There you go. Okay. So there it is. Now, to answer that question better, the question was what is flux? Okay. Another way to think about it is if you think about a solar cell, this is another helpful thing to think about. Imagine that this is a solar cell. Okay. Right now, wouldn't it be generating the most electricity? Right? Because the light is hitting it head on. And by the way, we talk about solar flux. We talk about this. This is actually something we talk about. We use the same math when we represent it, when we do that, right? Now, right now that we would have less flux? More flux, right? More electricity, yes? Okay, now watch this. If I rotate this, isn't it intuitive to you that we would actually generate less electricity if the sun's not hitting it head on? Okay, now look at the shadow of it on the screen. As I turn it to 90 degrees, you know it's 90 degrees when no light goes through the loop. Yes? So flux really is, the better answer to that is, flux is the sense that we've got magnetic field going through the loop. It's the amount that goes through the loop. Here, none of it's going through the loop. Here, a lot of it's going through the loop. Mr. Lucas, how are you? Okay?
How's everything?
It's good. All right. So here we've got the maximum amount going through the loop. Here we have none going through the loop. Here we have none going through the loop because we're not in the magnetic field. Yeah? Okay? So these are all ways that we can change the flux, right? And then yeah.
Isn't it easier way to just think about it, how much area is exposed to your magnetic field?
Right, exactly. How much area is exposed to the magnetic field? Yeah, that's what flux is, right? Okay. So now let's go to Faraday's law. We'll go back to that slide. I always argue about which way that slide should go, and I've switched them now. You know, there we have it. Okay. So this is Faraday's law. This shows you how to calculate this shows you how to calculate the voltage, right? So this little thing here, the little E of General Electric, right? We bring good things to life. Okay. This little thing here is, strictly speaking, called electromotive force. Now, this is the only time I'll ever write electromotive force on the board because I'm way too lazy to write it every time. It's like E-L-E-C-T. Am I still writing electromotive? Yes, you're only halfway through, right? M-O-T-I-V-E. Am I done? No, you got to write force. F-O. Right, there it is, right? So we always will abbreviate it EMF, right? Now, the thing you need to know is that that's the same for our purposes as voltage, okay? And I'm saying for our purposes because when I was in college, my professors, I'd say it's the same as voltage, and they say no, blah, 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 and I never understood blah, 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 blah. So I'd say, well, but that's the same as voltage, and they go, yeah, but it's blah, 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 right? So when you go to college and you stay in school, and you go to like graduate school, maybe you'd understand this, and you could explain the difference between EMF and voltage, and I think it has something to do with Maxwell's laws and calculus, okay? So yeah. Stay in school, kids. Okay. So this is equal to minus n, and we're, by the way, going to generally disregard that, times the change in flux, right, over change in time. Now, if flux is BA cos theta, right, the Uber formula becomes minus n BA cos theta minus BA cos theta, right? Isn't that a change in flux? Right? In general, the change in flux is your final flux minus your initial flux. Now, by the way, does it matter if you go initial minus final? Well, not if we're ignoring the minus sign. You know, like, it doesn't really matter. It's a change, right? Okay. The minus sign is something called Lenz's law that says that the change has to oppose, whatever this current is, has to oppose the change. Okay? And we're going to get at that and practice that at some length. Okay? Another way to write this, by the way, is also just NBA divided by T. Right? It's just National Basketball Association divided by time, right? Almost always. That, by the way, disregards the angle, you know, but there it is, right? And then one of these has to be a change. Something has to change. You can't just plug it in if it's not changing. Right?
How can you convert those moving?
You can't. You can't. But so a lot of the problems are just always at right angles, right? So we'll do examples of problems that do both, right? Okay. Yeah, and N is the number. BA is standing in for flux, right? Yeah? Yeah. Okay. Could be change in B, change in A, and then, you know, really it could be, we could add the cos, couldn't we? Right? But then it's not an NBA, you know? Can't remember that, right? Okay. There's something I was going to say, and it's gone now. I hope it'll come back. Oh, N. There we go. Thank you very much. Okay. Okay. So what is N? N is the number of windings. Okay. And if you're dyslexic, it's also the number of wingdings. Okay. It's like the same word for me. No. White is. This is room 37. Okay. It is the number of windings, and by windings, we mean the number of times the wire goes around the magnet. Yeah. Okay, so here we've got not as many windings, but still many, and then here we've got, this is technically a buttload, I believe, yes? Okay, very, very fine wire, and the more windings you have, the more EMF you get. And so I had to have a lot of windings to get this